Well, I don't know if everyone is here yet. I guess you can start. Yeah, so I want to show another example where also distribution is very important here. And that's in LLP for sure. Since the transformers came out, it's much easier to parallelize language processing tasks now as well. So what happened to transformers was pretty much what happened to ImageNet in 2012, I think, where we finally had a massive data set that could be used to train models that can be used for transfer learning in other visual tasks. So on other tasks for computer vision. And that made it much easier to train models for a diverse range of little tasks that didn't have data before, right? They had very small data sets. We can still get a pre-trained model in ImageNet and just do fine tuning in the last layer. And you still can get really good results with that. And what happened with the first transformers is that, well, especially with BERT, that we finally worked out a way to train the models. In this case, it was actually unsupervised, right? So we use a language model task in what you can see down here. You get a sentence, and you also input a mask. Actually, you input a mask sentence. So 15% of the tokens of this mask, of this sentence are masked, sorry. And we try to predict the words that were masked out, right? So it just like completes the sentence. Traditional language models are just like predicting the next word. And this is useful, but then people are actually predicting the first word as well and doing this bidirectional thing. And it's important, apparently, it's important to have the whole context. So if the model can learn how to complete these gaps in the sentence, it seems to generalize well for a diverse range of other tasks as well. So we basically have kind of this encoder-decoder model, right? That it encodes the mask input and try to decode it into the actual predicted sentence. And the last layer, you just have a softmax of all possible words they could have in each one of those tokens. So those models are actually quite big because they have this encoder-decoder architecture and they conserve the resolution across all layers, as we're going to see later on. They actually have way more parameters than the computer vision models. So yeah, the way we actually use them is that we actually only use the encoder normally. And that encoder gives you a set of features that can be used to learn an additional model, normally just a simple linear model on top of it. And it can cover a whole spectrum of tasks. So you can have like sentiment analysis just to say if the text is how do you say, has good or bad intentions, or if it's a root text, or if it's, yeah, or any kind of binary classification you can imagine with text. Entailment, similarity, where you just like put the two texts next to each other and get the model to compare if the embeddings for the first text are similar to the second one. You can have multiple choice answering, and basically compare them again and put it on top of a softmax. And here, normally you have like you sharing the weights of this linear model across all the answers, right? And the base of these encoders is just a set of repeated blocks that come all the way from the word embeddings to the hidden state and then to the decoders as well. And they're always the same. I think BERT used 12 on the base model and 24 on the large model, if I'm not wrong. But they're exactly the same. They have exactly the same size and they have exactly the same resolution. We're not gonna get into any position encoding, but it basically just tells you the position of each one of the images as an embedding as well. Then we got the self-attention layer, which you have a look at next, and add and normalize, which is similar to ResNet, and then it adds a layer normalization. Instead of the batch norm, you use a layer norm, because those models are so big that normally the batch size is really small and batch normalization don't work. Or it was just because RNNs could not work with batch norm, and so people in LLP are used to use the layer norm instead of the batch norm. But either way, it's normally used a layer norm instead of the batch norm, which is good for synchronization in case of this distribution, because you don't have to care about it. And then for each one of the encodings, you have a feed forward that, again, another ResNet and normalize, residual block and normalization block. And that's it. It's actually a very simple model, right? But it proved very powerful in future. So the decoder, as you can see, is actually very similar. So the idea is stack up these encoders, say 12 times in the base BERT. And then the output is still the same dimensionality as the initial word encodings. If you're not familiar with word embeddings, it's basically just a vector representation for each word, which is in a lower dimensionality as the words themselves. So if you could have like 1 million different words in a vocabulary, but we tried to reduce that to 700 dimensions. And this is done just by using a linear layer. It's a very simple concept as well. Then the decoders are basically the same as the encoders again, but they will have the linear model at the end with your softmax, which go back to each one of the 1 million words, let's say, in your vocabulary. And that's it. But because of everything is done with feed-forward networks now, it's much easier to parallelize, as before NLP was generally done using recurrent networks, which are much harder to train. Sorry, wrong direction. And let's talk quickly about the self-attention at a very high level. BERT, or the original transformer, already used this very well. This is a illustration from this blog. I guess you could call Illustrated Transforms. It's really cool, actually, a really nice website that has lots of models there, and it always does this kind of visual representation of what's actually happening in the math. And so even if you have the formulas, you normally you don't get the dimensions of each one of the variables. So you have to read the papers with a lot of detail to actually understand what they're doing, or you have to look at the code, right? And when you have this kind of representation, it's much more obvious the sizes of the things and how they actually get transported around. So basically the self-attention has these 3 components, which are 3 linear layers again, and it transforms the embeddings into this query key and values, and then does a matrix multiplication of the queries against the transpose the keys, and just scale that and use softmax, which normalizes everything, and then multiply it by the values again. So that at the end, this is gonna give you the same dimensions that you had at the input, but you have now these attention masks, which are completely non-linear because of the softmax. And if you get the softmax, you can actually print it and plot it more or less like that. So for this specific attention layer, you can see that it kind of models like similarities or the subject. So here it responds very strongly for the animals, which is the subject of the sentence. So you kind of have this, this language understanding, you could say, And each one of the layers seem to have different semantics in them. So people use this to try to explain the models. Other people say that it's actually not as powerful as it looks, but well, anyways, it performs pretty well on language model tasks and other NLP tasks. And I think that was it. Yep. Yeah, if you have any questions so far, let's see. No? Yeah, if you have any questions, please just write on Slack, and I'll have to stop the sharing. Sorry, I'll just switch here. And yeah, let's have a look now on one example of tasks. So we have this task from Stanford. It's the Stanford question answering dataset, so called SQUAD, which is basically trying from a paragraph, trying to find an answer for a given question and highlight the answer within the paragraph. So you basically finding a sentence within that paragraph that answers a specific question. First, we need to have a quick look on the tokenizer. So BERT is this word piece tokenizer, actually. But so the idea is that for each word, you can get an embedding, but because there are too many words, this gets really expensive. So people basically are just ignoring very uncommon words, and that gives you a problem at the end because you don't know what to do with those words. So what they do is say you can have embeddings for parts of the words and instead of the whole word. But at the end, BERT end up encoding most of the words as single tokens, as we're going to see at the end. Yeah, so looking at the data is provided as a JSON file, basically. And you can load it pretty easily from their website. And then for each entry on the JSON, you're gonna have a paragraph and a given set of questions and answers. And the answers basically have a starting point and some text. And this text is always from the paragraph, right? So you could actually have a start and an end instead of the text, but they chose to provide it like that. So we want to train a regressive model, which gives you two integer outputs. In that case, we basically want to have the start and the end. So you have to do that by hand, but the answer is in the data set, so it's doable. And those are probably questions done Mechanical Turk or something. So some are actually quite weird. Like this is actually wrong for me, but yeah. I don't think the Alpine region is known as 4000s, but it is a simple task for humans normally. It's given the question, you can just screen over the paragraph and find something similar and then find just the word or a little piece of the sentence there, and that's the answer, right? But still, if you go on the website, which we could open now, you see here the human performance. It's about 86% accuracy, and there are some models that perform quite a bit better than that. Right. So you have like that's an ongoing competition still, like people still submit to it. Although it was very much more popular at the end. Although there was quite a few submissions in 2020. Yep. Anyways, we're going back in here. So let's have a quick look. This whole notebook is based on an example that is given by Keras itself, which is also linked up here. And they very nicely provide us some code that can help generating your data set. So if you go to this quad, and there we have a utility file here where it does some pre-processing, and it's a little bit of code, not too much, but I can give you a quick high level on it. It's basically gonna get, as we said, oh, sorry, wrong notebook. As we said, we have just this start and the text. We need to calculate the end, basically. Which in this case here is just one token probably. So the start and the end is gonna be the same. And that's basically the pre-processing, but also those things are contained within the paragraph. So you have to like flatten it out. So for each question, you basically gonna have in your data set a paragraph, a question, and an answer, right? Very simple vectorizable thing and not this hierarchical structure. So you have to denormalize your data set. And generally, this is where you spend a lot of time when you're creating and trying to solve a new problem, right? As for a new task, you're tackling a new competition or whatever. And basically, this is all done in this function here, which is inside that. But as I said, we're basically generating this unnormalized representation of the same data. And we're going to have a quick look here. So now we have this three-dimensioned X train, and they all going to have the same length. So this is a good catch of the transforms as well. They have to work with a max length. If you're doing RNNs, you could work with any length that you want because you're training one item at a time. But now you have to hard code basically what is the maximum size of your sentence. And so this is in tokens, which is more or less 380 words, right? So you have to choose a number. And if you choose less than that, it means that you're cropping part of the paragraph or the question, and that could induce like in loss of accuracy, obviously, because you're not going to be able to answer a few questions. So it has to be large enough. But how you set that, it's depending on the data set. BERT itself does not accept anything above 512, sorry. But 512 words is already enough for many tasks, right? It supports like a reasonably large paragraph already. So what we have now, we need to have these paragraphs and the questions. And as we saw on the slides before, like the model only accepts one input actually. So we have to actually concatenate the paragraph and the question so that it's a single input. And when you tokenize it, you basically add integers for each word. And here you can't really see what's happening. It's just a bunch of integers, right? But the function that we used before also provide two masks, additional masks here that we have a quick look. So if I just decode first the initial sample, you're gonna see here that we have the whole paragraph at lowercase because we chose to, and the question at the end, right? And there is a separation token here in the middle, which is not a space, but it's in there. And we have to tell the model where the question starts and where the paragraph ends, basically, right? And in BERT, this is done by some masks. So first, there's the token type ID, which we get at input 1. And this mask is basically just the question, which is here. So you can, if you count the number of tokens here, it will be exactly the same amount of words we have here. It's 4, 8, 10. Yeah, you should have 4, 8. Well, they're actually 12. There's the question mark and maybe the quote. I don't know. But yeah, if I actually use the mask, so I just get in the ones in there and then mask the train 0 and then decode it, I get exactly the question. So it all looks good. And the second and last mask is the attention mask. which tells the model where the question ends, basically. So here you can see you have a bunch of zeros that correspond to also the zeros in the original encoding. So it's kind of useless. Like you could actually, yeah, it wasn't really necessary to have that. But that's the way they model BERT. So if you want to use BERT, you have to do that. Other NLP models might be slightly different. And again, this is only required because in this task, we actually have two inputs, right? So we have the paragraph and the question, as you remember. And because of that, you need at least the first mask, which tells you the position of the second input. But yeah, once you get that, that's it. That's pretty much your model ready. So the inputs are these three inputs that we saw, the original concatenated paragraph and the question, and then the first mask, which tells where the question is, and the second mask, which tells where the padding is. And the output is the position of the beginning and the the beginning and the end of the answer. And that's what you want to predict, right? So now we have here everything split up. So the context, as we saw, is the paragraph where the answer is, the question, and then the answer as reference. And at the end, you have here the position of the beginning and the end of the answer within the paragraph, right? And that's it. Was that somehow clear at all? Any questions so far? So moving on. So let's play with these already. You see now how we use that. So basically, once you have the data set in that form, it becomes a general deep learning model again. You have an input and try to predict an output, and you have your nice black box immediately. And that's basically it. So again, we're running the same code here again. We could have done it in a better, different way and store the output. So these will take about a minute to run if you want to run yourself. If you want to do NLP in real world, you probably want to save the tokenized output somewhere so you don't have to redo this thing every time. This is actually a small data set and it takes a whole minute already. If you have a large data set, it could take like an hour or more. But basically that's it. So to get the model, we're using Hugging Face now, which is a really nice library, which is the standard basically in LLP nowadays, supports both PyTorch and TensorFlow. Where is the import? And sorry, it actually comes as transforms, but yeah, it's called Hugging Face. And they basically have all possible NLP models. They are out there. Everyone that creates a new NLP model will put it there because it's the standard. So it's the best reference place you can go to. And once you get, if you call from pre-trained, it's actually going to download everything. And BERT base is already 500 megabytes. If you get the large one, I think it's probably a gigabyte or a bit more. So we provide the base model at this folder here, so you don't have to download it again. But the model is very simple after that, right? You have this encoder that comes from the pre-train, and you have to declare the three inputs again, and you give them to the encoder. So as we say, you got the input, the tokenized concatenated paragraph plus question, the token type IDs, which is again the mask for the question itself, and the attention mask, which is the concatenation of both. It just tells you where the padding is, so where you should not look at the question. And then from the encoder, you get the embeddings for the sentence. And the assumption is that you can just put a linear model on top of it, and that proved to be good for most tasks. You can try a more complex head, but that's normally doesn't really help much your model. So in our case, we actually have two heads, one for the start and one for the end of the sentence. And they're basically the same, just a dense layer on top of it. And then we flatten everything and we have a softmax on top. That's it. And you can see here that I'm only using the first output of the encoder, because the BERT actually gives two outputs. Actually, most NLP models will give two outputs. And the second output is basically coming out of the attention heads of the model, and doesn't really help you much. You could use it, but you will use way more memory if you do. And so I'm using cross entropy again. And once you compile the model, you get this weird warning here, but if you read it, it's fine. It's just saying that you're not using you're skipping 2 layers. It's basically because of that as well. And unfortunately, you can't see much on the summary of the model. It only tells you there is a BERT model there with 100 million parameters. And that's it. Right? It's not extremely informative. There's this really cool stuff from Keras, the plot model. You can see the 3 inputs, which should be connected here, but anyways, and we have the BERT model, and then the 2 outputs that come out of it. The dataset, again, now that we prepared it, it's very simple now. We have basically the 3 inputs that will come as X, and the 2 outputs that come as Y, and we can zip them, and you have your data sets that give you 3 and 2 inputs. If you see here, I print the first batch of it. We're using batch size 16, so we get 16 times 384, so 16 sentences 3 times with the 2 masks, and then we got 2 outputs of size 16, which are integers, right? So far so good. Oh, what happened here? Interesting. Yeah, we left an option here, and I think you guys saw generators with Rafael before, and you could use a generator to do exactly the same. I don't like it so much just because it's a bit verbosy, but if you want to do some more interesting stuff, you can use that. You see you have the same 3 inputs and the 2 outputs here, and you just have to give their types and so on, but it's basically the same. You're gonna get exactly the same output, but it's in the notebook again. So when you fit it, this one is gonna take a bit longer, but you're also gonna complain again that we're not using the polar. But the polar is what I was saying, basically just a linear layer of the last output, so it's normally doesn't really help you at all. So most people don't use it. TensorFlow complains about it, but it doesn't matter, and you can safely train your model. I've added accuracy as well in your model, as we saw here before, metrics. Although this is a bit misleading because we'll only calculate accuracy values for each one of the outputs separately. So you see, I'll have, let's see in the validation here, I actually have 2 accuracies in the output, but it's the accuracy of just the start and the accuracy of just the end. So yeah, it's not actually the accuracy of the answer, right? Which we need a helper method to calculate here. So the helper method is provided down here. We could have put it on the utils, but it basically just normalize the text, removing punctuations and things and extra spaces, and then encodes it and finds whether both the start and the end are in the correct places. So you have to be an exact match, and see the results after. The accuracy is 22%, the exact match, which is much lower than the partial accuracies that we had above. All right. And here we only trained, I think, 50 steps. And we already have a reasonable accuracy because obviously we're using this large pre-trained model. You can definitely do way more than that. If you train further, you get a better model. And yeah, so after you prepare all the data, it becomes a very trivial task again, right? You can see here that like you can see some were actually correct. Sometimes it misses the end. So yeah, some answers are actually related, but not exactly. And sometimes it doesn't get the end of the sentence at all. But it learns incredibly fast with only 50 batches of 16 sentences. That's pretty impressive, right? But the model is much larger than the models we were working before, so it takes much longer. As you remember, we're doing like half-second per step with a much larger batch, and with BERT we get 4 seconds per step, right? And because the data is much smaller, there is very little you can do on the host side, sorry, on the CPU, right? We're not doing any pipelining at all apart from just zipping them. So there's nothing going on CPU. So the task we propose is again to distribute that. I don't know if it's interesting to you guys, but either way, let's see. It's 2 o'clock now, so we're much earlier. I could give you guys another half an hour again, and then we come back to see if you guys have any questions. We're gonna have the question and answer session at 3:15 as well. But feel free to shout out if you have any doubts. I think it is useful to try yourself to run the models and distribute and see the profile as well. So you can add the tensor board here in the callback and see how the profile as well. We can see that after and come back. And yeah, that's basically it. So I'll see you guys at 2:30, let's say. So yeah, you know by now the solutions are on these folders. As I said before, I find it really useful to try to run the models by myself and see the questions you may have. If you still have some time, so you can go through the models and see. I wanted to point out something that in Harvard specifically, it looks like you cannot shard the validation set, although it has this metric average callback. It doesn't seem to be working correctly, and I'll probably report in their website later on. But you can see here that the validation is not the same on both nodes, and that's the whole point of the callback. So you should be able to shard your data set, your validation set, and you only need to validate half of the data on each node. So if you have 10 nodes, you only need to do 10% of the validation. In this case here, the validation itself takes about 2.5 minutes to run already, which is not much, but it can be annoying if you have to wait for that every time to look at your results. And So it's very handy if you can actually split the data between the nodes, right? They're waiting for the data anyways, instead of having to run the whole data set on every node. And this callback is meant to synchronize the results. So here you should actually see exactly the same results on both. And to do that, you actually need to do the whole data set without sharding. And then obviously you're gonna get the same result because the whole data set is run on both sides, right? I'm gonna quickly update that and push it over. There's also linking missing on the file system, so yeah, so you wouldn't be able to run this from the folder as it is. I'm gonna push these two little changes right now, but yeah, apart from that, I've added also the tensor board here again, and you can see the same profiling stuff that we saw before. On Harvard, unfortunately, you don't see much of the distribution going on. So as we saw before with TF, the TensorFlow distributed strategy, you can see all the all-reduce calls being executed in the host. And here, I don't think they actually map to anything. Yeah, I don't think it is. But yeah, you can still see the stats of all the models. You see, obviously, the model is basically just matrix multiplication the whole time, because the dense layer is also basically just a matrix multiplication. But that's about it. Like, if you see the input, there's not much going on the CPU side. It still takes some time, but you can't really do much about it, I think. Because basically, see, if you look at our data set, we're not really doing anything, right? So what you could do is maybe cache this. If you add a cache at the end, it doesn't have to go through the arrays every time. Especially the sharded run. Because the data set is small, you can cache the whole thing in memory. Especially if you had to read this from the file, right? But well, that's about it. Unless anyone has any questions, I guess we would finish a bit earlier, actually. If you see on the distribution folder, there are a bunch of other files as well. So if you see here, yeah, we showed everything in this course on JupyterLab, and it's a great tool to do your modeling. But if you actually want to do, for example, hyperparameter optimization or hyperparameter search, and you want to run lots of jobs with more or less the same model, you basically probably want to create a submission script instead of using JupyterLab. Why would you do that? Because you can run several of them in parallel without having to go manually through the interface, right? And it's, yeah, you have to make your code a bit more reusable by doing so normally. Try to avoid copying the same model over and over and just use includes, imports, right? And here, so you have using distribution strategy, you have the Harvard script as well, which is very similar. And then the same thing for the notebooks, right? We also added, addition to that, the Keras benchmark script that I could quickly show you. This is actually basically just a synthetic data set. So it has all the arguments and parsing in the beginning, but it's not very interesting. Where the thing happens here, basically generating some random data, and we're fitting a model to the random data with random labels as well, right? So it's kind of useless, but this gives you very clean benchmark because it's only using the device, really. It's not reading any images. It's not, yeah, well, you still have to send them as you used to, but yeah, that's basically how we would like to benchmark our process, right? And here you see we have our metric callbacks and the global callback that you have to do it. And we add this timing callback, which is going to calculate basically the total images per second that can be processed. And we do exactly the same then on the TensorFlow distributed strategy. So you got exactly the same code. We can easily compare the two if you want to. And I run the result. I probably should plot a graph with that, but yeah, basically the conclusion is that the Harvard is seemingly faster for just a few GPUs, but it seems to be a bit slower than distributed strategy for much larger clusters. So if you're using 30, 60, or 100 GPUs, it seems to be much slower. I want to confirm those results before make them public, but I'll add a graph here in our user guide as well later on. But yeah, I think that kind of concludes our tutorial. Don't know if Rafael is online. He wants to add anything.
No, thanks.
Okay. So do we still meet at 3:15 for the question and answer session, right?
Yeah.
All right. So guys, enjoy your break. Think about questions that you may have. You can play again with the notebooks and see if anything arises. Yep, well, you know how to find us. Thank you.